Good afternoon, everyone. My name is Sai Aditya Pradeep, and I'm the Scientific Program Manager of AIM, EFRC. Welcome, everyone, to the AIM Ideas Summer Research Program. This is the first webinar in a series over the summer where we'll be engaging with specifically students of South Carolina State University under Dr. Swain. And this whole program is brought to you by our Thrust 2. So Haizo Wen, our PhD student under Dr. Zen Lee, will be leading these webinar series. This is a series that is collaborated by AIM as well as Ideas NRT. So it's a collaboration between funding received by the US Department of Energy, the Office of Science, as well as the National Science Foundation. A little bit about these two programs. So the mission of AIM EFRC is to build an AI-enabled inverse design approach for fundamentally understanding and integrating material manufacturing design of advanced polymer composites. The IDEA's NSF NRT traineeship focuses on training the next generation of STEM students to develop expertise across multiple disciplines, specializing in AI-enabled inverse design, advanced composites, and manufacturing. This introductory webinar series explores the transformative role of neural networks in science and engineering with a focus on their growing potential to revolutionize data analysis and computational modeling. As a powerful branch of artificial intelligence, neural networks serve as surrogate models capable of efficiently approximating complex systems with high accuracy. This first webinar by Haizo will provide an overview of the fundamental principles of neural networks, emphasizing their versatility across different engineering applications. This includes predicting the behavior of composite materials, optimizing the design process, and supporting biomedical analysis. So with that, I'd like to thank Haizo for the webinar and Dr. Swain as well as the students at South Carolina State University. Thank you. Go ahead and share your screen, Haizo.
Okay, so today we are driving into the exciting world of AI. So the first topic is aimed to introduce the fundamental concept of the machine learning, especially focusing on its versatility in manufacturing, material design, and semi engineering, and some of the content are biomedicine. So a little bit of remind, this is our first webinar of summer research program. So there are other two hands-on tutorial webinars in July. So in the later two webinars, we're gonna learn how to use and program machine learning codes in Python. So today we're just focus on the introduction parts and to show you the multiple scenarios of scientific research and engineering process that we can apply neural network-oriented machine learning. So to start, so let's define AI. So artificial intelligence refers to the simulations of the human intelligence in machines programmed to think or learn like humans. So AI has evolved significantly since its inception, with application range from simple automations to complex problem-solving tasks. So divided by the stage that in the evolution of the AI process. So we can separate AI into different types. So the first stage is narrow AI, which perform specific tasks. It can match or even outperform humans in one specific task. So many mature AI models and algorithm has been already applied in the area like media recommendations, face recognition, self-driving in modern car industry. And the second stage will have a general AI, so which can ideally perform any intellectual task like as a human can. So general AI would have the ability to understand, to learn, and to apply knowledge across a wide range of tasks, just like a human. So currently, a large language model, for short LLM based generative AI, like those tools like ChatGPT, its underlying model like O3, O4 can be considered as the early models of general AI. Even though those AI have a very good reasoning abilities, but we still have a very large distance to real general AI. Ultimately, we would have a super AI, which is supposed to surpass any human intelligence in every field, including creativity, decision making, and emotional intelligence. So it will be smarter than the best human minds in every way. But those are just exist in the sci-fi movies. Like for example, just like the Jarvis in the Iron Man movie or the Skynet in the Terminator movie. So under the big picture of AI, machine learning is one among many specific areas. Data-driven is the core concept of the machine learning. It means that we can teach computers to learn from the data instead of programming every rule manually. We let the system to learn the patterns and make predictions. So here is a simple example. So if we want to design a module in a thermal system to determine the thermal status, so in the traditional programming, we would explicit the rule to the machine. So machine would just follow the rules that we just define. But for machine learning, we don't define that. We just give a data set to machine, and there's a machine learns the pattern of the temperature and the thermal status, eventually predicts what would the thermal status would be if the temperature value is not inside the original data set. And under the framework of machine learning, deep learning is one of the most popular ways that is commonly chosen for machine learning tasks. So the model of the deep learning lies on the framework of the neural network, and the concept is basically inspired by the human brain. So the adjective deep refers to the use of the multiple layers of neurons inside the whole network. So the whole process is that the raw material come in at the input port, and through a series of a mass operator inside the neural networks, the target output just come out. So if we use the previous example, like to determine a thermal status according to the temperature, so the input is the temperature and the output is the status of a hot or cold. So one of the main things about deep learning is that it can automatically extract the features from the raw data. Thus, we don't need to do anything manual. So if you consider the whole networks as the black box, the only thing we need to do is to set up the input and the output. But how does the neural network, or in short, NN, has the ability to learn the pattern inside of the data set? Or to say, how does the NN find the relation between the input and output? So in the perspective of math, the input and output data is nothing but a series of a group of number. What we want is to find the mapping or the function between the input and output. The universal approximation theory tells us, so for any continuous function like small of x and any error tolerance larger than variable, there should exist a neural network like big of x with at least one hidden layer such that the gap between the two functions, which should be within the range of small error. So that there is always an representing the big of x to approximate the small function of some f of x. So this concept is kind of similar to the math series that we learn in the fundamental math class. So we know that if given a continuous function like f of x, we can use Taylor series or Fourier series of multiple base function terms to approximate it. And using more terms and adjusting the right coefficient like an here in each term, the approximation result would be closer to the target function. So the idea is to use approximator consists of a series to approximate the target f of x. So the NN is based on the same idea. So for the NN, math series are replaced with the structure of the neural networks. So the base function terms are replaced by the neuron inside the NN, and the adjustable coefficient AN are also replaced by the weight and biases in each neuron. So the evolution of the approximation quantity is represented by the loss function, which is defined as a gap between the prediction and the target function. And what we want is trying to minimize the loss function as minimal as possible. So the NN is doing the same thing, which is to approximate the target function. So the lower the loss we have, the better approximation we would get. Not only limited in the range of mass and functions, and then approximation ability can use for a more complicated and abstract scenario. So a very classic example is the image identifications, where we insert the image of the animals as the input and the NN to determine which one is dog, which one is cat. And complex problems like image classifications, natural language processing, speech recognition, auto drive forecasting on complex time series can be efficiently solved by NN-based models. So the reason that NN has a strong generation power for a different or complex scenario is because NN has a high adjustable complexity. So NN can be really complicated with thousands or billions, even trillions of neurons. So this allows NN to have the ability to deal with a super large amount of data. So, however, the advantage of NN sometimes can be a disadvantage because collecting and organizing a big data set for training is not very easy. And training an NN usually involves with the massive data, and the neurons usually like consume a lot of computational power. So people start to use more efficient hardware like GPUs or TPU to do the NN training. And how to reduce the training cost and use a smaller NN model to train large data set is one of the ongoing and important direction that research people are working on. So since our main topic today is scientific machine learning, let's take a step back and think about how humans solve the scientific and engineering problem in the traditional ways. So for centuries, we've relied on the power of the fundamental physics. So those physics laws, like Newton's laws of motion or Navier-Stokes equations, are beautifully compact mathematical descriptions that governs everything from the falling apples to the turbulent fluid flow. So these laws enables us to design like bridges, rockets, smartphones, and any modern designs that we know. So the extension of the boundary of fundamental physics and the inventions of new design are usually come from the decades of research. So conventionally, there are two ways. One is to conducting actual experiment, and another is running the numerical simulation based on computers. So these methods are powerful, but they can sometimes can be very expensive, time consuming, or limited by the computational resources. But we may have a third approach, developing a surrogate model using neural networks. These models doesn't replace physics, instead they learn from the data, either from the experiments or simulations, and offer a faster way to like approximate physical behavior or engineering process. So surrounding the scientific machine learning, we can use NN to explore the hidden physics to push the boundary of science. We can also use NN to solve engineering problems in a more efficient way. We can also use NN to assist our modern engineering design. So in this following content, I will introduce four like specific topics to elaborate how to use different NNs to solve a variety of engineering and scientific problems, and hopefully give you some insights in how to incorporate NN into your own research or engineering design. So let's first talk about the composite materials. So things like carbon fiberglass or reinforced polymers. Over the past few decades, scientists and the engineers has been designing new structured composite materials to meet the growing demands of the modern technologies. Researchers began combining like multiple materials, taking the best properties from different components to create a composite that are stronger, lighter, more flexible. For example, in aerospace or in automotive industry, using a composite instead of a conventional metal can dramatically reduce the weight, improve the fuel efficiency, and even enhance the safety. When people came up with a new design of materials, the first thing we would naturally do is to test the mechanical performance of the material to see whether the property of the new design material reach our expectancy. One of the commonly like employed and the cheap ways is to conduct a finite element analysis by giving different levels of patterns of load in simulations. Designer can pre-examine the deformation of a pattern of their newly designed material, thus validate their design's reliability and eventually improve the design. So even though compared to the actual experiment, FEM simulation would save a lot of time and money, but sometimes a lot of simulation, especially the one involved with very complex geometry and multiple material components usually take a lot of time to finish. So our motivation here is whether we can develop a surrogate model to replace this process. If we have a well-trained NN, whenever there's a new similar material, so we can just insert the material into our NN model, and instantly we will get the result. If we try to use simple math language to describe the F-even process, so there should be a load function that we should give to the material. And so in response, material will produce a response function. So our mission is to develop a surrogate model to approximate the mapping between the load function and the response function. So in the regional math, we refer a mapping that turns one function to another function as an operator. So the simplest example is a basic differentiations and integration that we learn in math. So if we do first differentiation on the x squared, we will get an outcome of a 2x. Both input and output are in form of a very specific function. So back to our NN, just we learned before the universal approximation theory that ensures there's always an NN that can approximate the mapping from mapping f from x to y. So if we extend the concepts, the x and y, to the function a and b, so theoretically we can build an NN-based operator to map function a to function b. So therefore we can build a deep neural operator, or DNO, to approximate the mapping from the dynamic node function to mechanical response function. So the structure of a DNO is composed of two major parts. One is a branch net that takes load value as input, and the other one is trunk net that takes unchanged time sequence as output. If we consider there is a dynamic strain node, the load function has strain on the y-axis and time on the x-axis. So for different node patterns, the strain value on y-take is changing, while the time take on the x-axis is not changing. So by multiplying the two matrix products from the two nets, we will get an outcome sequence, which is a mechanical response sequence. So after knowing the structure of the model, here is the general process of the problem set up. So since NN is a data-driven, we are going to release a lot of data of node function and corresponding response function to train our NN. So therefore, FEM simulation is conducted to provide data and also provide reference for comparison. So those data are fed into the NN model. Once the model is well trained, it should predict a response function given a random dynamic node function. So we built a beam with a composite steel and aluminum material. We gave dynamic stream node function as a free ending of the beam as the input of simulation, and therefore there should be a response temporal force function as a fixed end, and the normal stress distribution along the x direction as the output of the simulation. After the simulation, the input and output data is given to the DNO models to train. So this is the dynamic force prediction result given by the DOM model. After the model is well trained, the average accuracy is around 98%. So there's only some local misalignment. So but the overall prediction is very accurate and proves the DOM model is pretty reliable. So the stress prediction also looks pretty good in both compression and tension deformation pattern. And the average predict accuracy of the model is also around 98%. The relatively large error can sometimes be a reason of plastic hardening, since we introduced the dynamic node, and the plastic mechanics is nonlinear and sometimes will be very hard to learn by DON. So there should be some manual error in the result. So the test to find the relation between the model's performance and the size of a training data set is very essential in training a surrogate NN model. So in our DON model, in the case of a beam mechanics, dataset with size of 2,000 to 3,000 is the best choice, which offers a very decent accuracy with a mid-sized data. So whenever you design your own NN model for a scientific or engineering problem, this step is always a priority because it helps you to determine what size of a training data you should give to the model with high accuracy and low cost. And the DNO model is also faster to train than the conventional deep neural model. If the code is implemented in JAX, the training speed will be even faster. And another key element you may consider as a priority to test the NN structure for own problems, because sometimes the higher complexity of the NN structure doesn't always guarantee a higher accuracy. So every time we build and test an NN, we need to find the optimal structure. So in our case of a DOA model, the 3 hidden layers and each layer consisting of 200 neurons are the optimal structure. So one thing to mention is that the robustness of the neural network model is also very critical. If the training data is obtained from the experiment data with some noise, so the error generated due to the inserted noise less than the percentage of the noise. So this shows our DNO model demonstrated robustness in this task. Test of the robustness is also very necessary because in the real world engineering process, there's always some inevitable noise to introduce the error in the data set that you collect. So the high robustness or the stability of enable your NN model more convincing. Sometimes you will find your NN model's performance gets significantly worse when there's a small portion of small noise you put in the data set. It means you may need to we may need to reconsider some import some modification to make your model more robust. So to summarize in this topic, our DNO model is fast, robust, and accurate. Through the first topic, we learned the structure of DNO is suitable when approximating mapping between the function to functions. In your own research or design for engineering process, if you found two important functions that share correspondence, this may indicate you to try with DNO structure. So our second topic lies in something about biomass. So the biomass is a key player in the development of sustainable energy and materials. Among like various types of biomass, the corn stands out as one of the most widely used crops in the world. Beyond its role in the food production, corn and its byproducts are also very valuable. And sometimes it makes sometimes it makes very important resources in the renewable solution. But before the biomass can be transformed into very useful fuels or chemicals, it needs to go through like several pre-process steps. And one of the most critical steps is the size reduction. So why does this process so important? Because the raw biomass like corn stalk is bulky and different to process directly. Reducing its size can improve the handling, increase the surface area, and enhance the efficiency of certain like downstream process like chemical conversion, fermentation, and combustion. So in short, the size reduction in biomass pre-processing is very important for converting a raw agricultural residues into a clean energy and valuable products. So to investigate this problem, we cooperate with the at our national lab to study the biomass size reduction process. We know that with the increase the area to volume ratio, it's more efficient to biofuels the synthesis, but harder to storage as a biomass of corn, which is easier to get wet. So the size reduction process can also cause jamming and the equipment shutdown. So if we can understand and predict the size of the reduction process, so we can prevent the plugging and improve the efficiencies of biofuel production. So here it shows this is a machine that composed of a different like major components. So it has the hopper and the mill throat for the raw biomass to go through, and the mill chamber to cut the biomass. The screen is placed at the bottom of the mill chamber to control the output milling size. The grilled biomass finally will drop into the container to container for people to collect. So for many years, the successful like proceeding of milling process highly depends on the experienced workers who has been like operating this machine for more than 20 years, and they know exactly how to change the machine parameter when the machine is like jammed or plugged. So we worked with Idaho National Lab to say whether we can use machine learning to help improve the milling process. So just like we did before, we want to simplify the milling process into the basic math language. So that may give us a hint about how to design our NN model. So the key process of the milling is to reduce the particle size of the corn biomass. So we can use a cumulative distribution function. So to describe the size of the distribution before milling and after milling. So before milling, the raw biomass have a larger particle size. So distribution is in a large range of like 10 millimeters to 30 millimeters. While after milling, the particle size of the safe size gets smaller. So that's the distribution of the size is smaller than like 5 millimeters. So we still use a previous mindset. We will find the milling process is very essential. The mathematical mapping in the feed row biomass curve distribution function to output biomass cumulative distribution function through the milling machine. So therefore, we can still use a framework of our DNO model. So different from our previous composite beam case, so the milling process of a biomass is involved with external parameters. So experienced worker would automatically know what would the rough product look like by knowing which screen size and the milling machine is using and how moist the raw biomass is. So we need to modify our like DNO to DNO plus by incorporating this influence of these parameters. So therefore, we add an additional parameter net to inform the neural networks with the parameters information. So here we can say the predicted cumulative mass distribution of a corn biomass from the DNO plus model. So the prediction aligns very well with the reference data, achieving about 99% of accuracy. So this means the model does a very good job in capturing the overall trend of how biomass accumulates across the different particle sizes. So the high level of agreements show the DNO plus model is not just fast, but also very reliable for approximating the biomass size reduction process. So however, in the reality, collecting biomass data to train a surrogate model can be very time consuming. Even after several years, the amount of high quality but useful data that we have is still less than like 100 samples. So to address this limitation, we're looking into developing a model that could work with less data. So that leads us to explore like physical informed DNO plus models or PI-DNO plus model. In this way, we use the population balance model, which is a simulation model, to expand the size of a data set. So that's reducing the need for large amount of data from the actual milling experiment. So here we can say when we apply PI BUM plus model, we can say they predicted the cumulative mass distribution for biomass compared to the original one. The accuracy is slightly lower, about like 90-70%, but still very good result. So prediction continues to align very well with the reference data, meaning the model still captures the overall trend of the how biomass accumulates distribution function across the different particle sizes. So even with a fewer data points from the actual experiment, thanks to the PPN's models data interpretation, the models remains very reliable and efficiency in approximating the size reduction process. So the DON plus models includes an additional parameter network, which allows it to incorporate the influence of important external factors, and it performs very well under these conditions. We also couple the DON plus model with PBM simulations. So that's gonna help us to reduce the neural network's reliance on the large amounts of training data, making it much more efficiency. So, and this result highlights the strong generalization abilities of the DON framework, which is flexible and adaptable. So for the third topic, so let's begin with the governing equations, which are the heart of the most physical models. So those equations are really written in the form of partial differential equations or PDEs, and they describe fundamental physics laws, things like conversion of mass, momentum, and energies. So PDEs are incredibly important because they help us model a huge range of real-world phenomena, from fluid flow to heat transfer to wave functions and so on. Now, usually solving this equation exactly is often impossible, especially in a very complex system. And that's where we use numerical simulation to use as an alternative approach. So numerical simulations for PDEs form the foundation of the modern computational simulations. Well, whether you are designing a race car or thermal radiation system or aircraft, you are likely to use those simulations to solve PDEs. So when we talk about the classic PDE-based numerical simulation, is always a conventional mindset. So the first step would be to clearly define the physical problems using appropriate governing equations, usually in the form of PDEs. So these equations capture the core physics laws involving the system, like fluid flow, heat conduction, and wave motion. Then we're gonna build the geometry of the system and apply the necessary boundary conditions and parameters. This means setting up things like domain size, wall inlets, physical constraints, and material property, and so on. And the final step is to solve the PDE numerically using the methods like fundamental elements or finite volume. The results is a numerical solution that approximates how the system behaves over space and time. So softwares like COMSOL, ANSYS, APCAS, OpenFOAM are usually favorable by engineers and researchers. And if you are good with coding, you can even write your own solver. This mindset has driven decades of programs in simulation and is still the backbone of the most computational physics tool today. So, but as the problem get more complex, the data become more available. Researchers start to looking for new ways to complement or even rethink this traditional pipeline. That's where the machine learning comes in. So at first, it was used to assess the simulations. So one example is to refine the resultant physics field resolution. This is a simulation run in low resolution, and the machine learning incorporates the result into a higher solution one. So thereby reduce the computational effort. Another one is to use machine learning to automatically generate and optimize the version. But in recent years, we have seen a growing trend where machine learning is used to directly solve the PDEs. And this brings us to today's main focus, the PINN, which is the physical informed neural network. So PINN bends the structure of the physical laws with flexibility of deep learning. It offers a new approach to solve the forward and the inverse problem. Often in the solving process, we can use less data and don't use the discrimination process at all. So let's take a closer look of what makes the PIN so special. So just like I mentioned, the sense of a governing equation or PDE-based simulation is to solve the PDE by numerical means. So if we assume there's a PDE in the simple form, our mission is to find the solution in the form of f of x, y, t. So if you really think about the mass essence of the solution f, it is a mapping after x, y, and t into a result u. So remember what we talked about before, we can use a surrogate model or surrogate NN to approximate this mapping based on the universal approximation theory. And by minimizing the gap between the NN's prediction and the real solution, we will get the approximate NN solution. But what makes PNN so special is that the model introduces the additional physical information from the equations and or as the physical constraint to regulate the approximating. To say we're in the process of training, where the blue NN mapping is not good enough, but is still evolving. So in every evolving state, we can extract the local partial derivatives through automatic differentiations. So this derivative should by PDE. To say in math, the operation result of this derivative should be 0. So therefore, we can define an extra loss to quantify how well NN's derivative satisfies the governing PDE. Therefore, we can impose the physical constraint to our NN model. So the mission should be to minimize the total loss from the original definition of the loss function and also from the PDE. Another important thing to notice is that when automation tries to minimize the original loss, we need to know the exact value of the reference value in the field. Since the NN's mission is to find those values in the field, and the only priority known value we can use for is at the specific boundary condition and the initial condition. So the training data in minimize the original blue loss here is sampled from the boundary condition and initial conditions. Meanwhile, if you think the definition of the physical loss, we don't actually need any known field value as a reference. So the training data for the red physical loss can be just a sample from anywhere in the whole domain. And that is a very important thing in using PINN. We need to know where to sample the training data. So basically, PINN is approximating the solution of PD in both directions. So the predicted solution should look like a real solution, and the predicted solution should satisfy the PDE. Here we use a very simple case of a heat transfer to demonstrate how we use PINN in solving PDE. So if we consider a 2D squared domain without any heat source or sink, the governing equations would be in a form of a simple Laplace equation, or representing the steady case, and a Poisson equation representing transience cases. So we consider the material inside the domain has a constant thermal properties, and the value of the properties is self-defined. So the PDE would look in a very simple form. So for comparison, we use composite to generate a reference solution of the 3 steady cases and 1 transient case. So the three steady cases on the right side are given different boundary conditions on the right edge of the domain. So the transient case on the left side are simulating the temperature field change from dimensionless time from 0 to 1. And this is a solution result that predicted by the PINN compared to COMSOL result. So you can say the two results are really close to each other, and the overall accuracy of the PINN is around 89% to 95%. So the only mismatch is the marginal area in the 4 corners of the domain. So, which is understandable since large gradients would generate in the alternate areas between the 2 boundary conditions. So that means the COMSOL may give an inaccurate solution in this area as well. But if you look at the overall trend, the overall production is very good. So the rest one steady case and the transient case also show the same high level of accuracy as well. So this means PNN can solve a PDE just like a conventional numerical simulations where we know the PDE form and only the boundary condition, so we will get the result. So those results are showing the capability of a forward PNN, which is to solve the PDE directly. But PNN also shows something very unique, which is the inverse discovery. So let's try to imagine a scenario where we invent some new materials and we want to find out what is the thermal property of the new material. And the challenge really lies in we may not know which term should appear in the thermal equations. So it would hard to directly determine the thermal property of material. So the mission of the inverse PNN is to help us to fix this problem. So since we can use optimizations to determine the weights and biases in NN, we can also put the undetermined thermal coefficient into the PDE. So during the training process, all the weight and biases as well as the thermal coefficient are going to be optimized. So we let NN tell us what coefficients are the optimal ones to match the PDE. So the results show, so this is the result. So results shows the two scenarios. Scenario one is we have physical institutions to say we know what the exact form looks like. We just don't know what is the value of the coefficient. So inverse PIN can help us to determine the exact value. The prediction coefficients are very close to the reference value of 0.1. Another scenario is just what I said before. Is we have no idea what would the effective terms will be like into equations. So will be the first derivatives or the second derivatives? So we don't know. So the inverse PIN will solve our problem if the term is not effective. A very low coefficient will be given the equation. So the PIN is very powerful in the engineering and the scientific problem related to the PDE solving. But more importantly, PIN really gives us a hint that we can incorporate the additional information into the NN in the form of a constraint, thereby to improve the NN's performance. To say if you are trying to use the NN to approximate some engineering or scientific process in your own problem. So is there any physical laws or constants that can be that in the process now, in the process, or is there any constant variable that exists in your process? So this kind of thinking might help you to improve your NN. And the fourth and the last topic today is in the regime of biophysics. Like specifically, we are going to talk about the red blood cells or RBCs. So RBCs are most common cells involved in the blood circulation. They circle through our body's circulatory system during their normal lifespan of 120 days. So they transport the oxygen from lungs to other tissues and organs. RBCs naturally has a shape of the bioconcave and highly deformability to pass through some narrow capillary channels. So the morphologies of RBC can be seen a very vital indicator of a circulation health. So the basic logic is that if the RBC displays an abnormal shape, it is highly caused by some pathological factors, which also influence the regular mechanical properties of RBCs and eventually their deformability. RBCs would become hard to pass through the narrow blood vessels, thereby causing some blood disorders like SAA or malaria. Except these horrible diseases, the morphology change also occur in the normal aging process of RBC. Therefore, scientists have been investigating RBC morphology for many decades. So as computational methods and numerical simulation become popular, so scientists and the research people are building different kind of numerical models to produce a variety of simulations to study the dynamical behavior RBC in many scenarios. So these research are pointing out that an accurate and well-configured RBC is 3D geometry. before the formal simulation is very important because it might determine whether their simulation is correct or not. So the conventional experimental approach to obtain the RBC 3D geometry are very reliable, but sometimes it is really be of like high cost. So people naturally think the machine learning would help to reduce this effort. So researchers, especially like people from the computer science, so they build up a different kind of NN models that directly reconstruct RBC geometry from 2D images. However, most of the models lack either the generalizations or the efficiency. So we are thinking, would there be a smarter ways to do this job? So let's just put the background of RBCs aside for a little bit. Let's ask there a new NN framework that is a multi-fidelity neural network, or to say MFNN. So MFNN deal with two kinds of data set. One is the high fidelity data, and that comes very accurate and detailed but expensive sources. So in contrast, the low fidelity data is cheap and easy to access, but less accurate. And the two kinds of data usually share correlation. For example, if we previous in topic 2, in the topic of a biomass, we combine both actual experimental data and the PBM simulation data to train the DON plus. So if we put those data here, the actual experimental data can be considered as a high fidelity data, and the simulation data can be considered as a low fidelity data. So here I use a very simple mass function example here to show you how MFNN works. So there are two sets of data. The blue dots are high fidelity data, and they are very few but very accurate. The blue is a function that we want to approximate. So in contrast, the red dots are the no fidelity data points, and there are many, and the red line behind them is a low fidelity data function. So the two functions share some sort of a correlation. So if we use two separate NNs to approximate two functions separately, the blue high fidelity data one will naturally fail because we don't have many data points over here. So the idea of MFNN is that we can use the correlation between the two data sets, or to say we can use the experience of how the low fidelity data approximate to help, therefore to provide help for the approximation of high fidelity data. So thus we can design our NN in this way. So the neural vector in the red box will know the experience in how to approximate no fidelity function, and the neurons in the neural vector in the blue box will know the correlation between the two functions. So using MFNN, the high fidelity approximation result is pretty good. So since we know the basic principle of how MFNN works, but how do we relate it to the RBC geometry with construction? So in our previous research, we investigated the relationship between the RBC geometry and RBC biophysics. We have conducted a simulation where RBC deformed from an initial sphere to multiple stable shapes that gave in the process we gave in different biophysical properties. So just like the animation here, so the RBC deformed from a sphere to a stable shape. So in the field of mass, so as the inputs of the simulation, we will have the list of coordinates forming the sphere shape. And at the output of the simulation, we would have another list of corresponding coordinates forming a stable RBC shape. Thus, we can construct an NN to approximate the simulation process. So the thinking is, if we have one simulation that generates one RBC shapes, whether we can use one simulation as a no fidelity case to help to generate the other RBC shapes in other case. So which can be seen as the high fidelity data case. So relying on this idea, we build the MFNN using both subscene and FNN to predict the variety of RBC shapes. So In no fidelity CNN, we gave sufficient data points to approximate the no fidelity RBC reference shape to allow the no fidelity mapping can be fully approximated. Then we insert partial, or to say insufficient data of our target RBC in high fidelity FNN. The partial data is sampled from the RBC 2D cross sections because we want to mimic the reality of the experimental observation where only 2D images data are observed at these at several fixed angles. So this is a validation result of the partial CNN part. So as you can see, the sufficient data point with the sufficient data points, the low fidelity reference RBC shape can be fully learned using CNN. However, the approximation would fail if we directly use a single CNN with cross-sectional data. So then we have the result of a full MFNN predictor. We have tested a variety of RBC shapes. We found out that dissimilarity between the no fidelity reference shape and the high fidelity target shape are very essential. It means that two shapes should share some sort of a geometric similarity. So we use reference shape in the same category with the target shape to reduce the initial dissimilarity. Following this principle, FMN prediction with at least two cross-sectional data gives a very good prediction. So the overall average accuracy is around 95%. So MFN already gave us another hint that we can utilize the correlation among the correlated data set to refine our surrogate NN model. So to conclude our introduction today to scientific machine learning, so here are some takeaways. So the NM is nothing but a universal approximator. It can help mapping any functions or mappings. When we study an engineering or scientific problems, always try to deduce the problem into the simple math language first. So try to ask yourself, can our input and output of a study process can be described in a simple math or simple functions? Is there possible to use the mapping to connect them? So the DNO is very powerful tool to approximate the function to another function. And the key external factor can be concluded as well. So the PNN is also very powerful in solving PDEs and inversely discovering undetermined PDEs. And it gave us hint that we should always look for the process constant or provide additional physical information for our NN model. So finally, the MFNN, just as I mentioned, gave us a hint that we should use a correlation among the dataset to enhance our surrogate model. So that's all the topic content I want to share today. And finally, I would like to thank the AIM ERC Center and the Inverse Design Training in Ideas research program for giving me such an opportunity to present you this webinar. And also thanks DOE for funding and all the institutes and the universities.